In section 1.3, we're going to talk about our trigonometric functions from a right triangle perspective. So considering a triangle with a perfect right angle, we're going to think about one of the other two angles, the acute angles, and we're going to call it theta. So this angle here. Relative to that angle, the sides of our triangle are going to be one of them opposite. The one that is across from the angle theta is the opposite side. The one that kind of runs along it, beside it, is the adjacent side. So for my theta, this would be the adjacent side here. And the long side, the one opposite the right angle, is always the hypotenuse. Always going to be the longest side of the triangle. So using the lengths of these three sides, we can form 6 ratios that define our trigonometric function of the angle theta. These functions are defined this way. So it's important to note that this angle theta is in the first quadrant. So it is less than 90 degrees, so between 0 and 90. And for all of these angles in the first quadrant, our trig values will be positive. So sine is the opposite side over the hypotenuse. Cosine is the adjacent side over the hypotenuse. Tangent is the opposite side over the hypotenuse. And the bottom row are just reciprocals of those first three functions. So cosecant is the reciprocal of sine. So if I just take that fraction that I have for sine and flip it over, I've got hypotenuse over the opposite side. Secant is the reciprocal of cosine. So if I took my cosine and just flip it over, I've got the hypotenuse over the adjacent side. Cotangent's reciprocal of tangent, so it's adjacent over hypotenuse. So let's use these definitions. In an example here, we have this triangle. We've got our angle theta labeled, and we have the lengths of two sides. And we're going to try to use those definitions that we just saw to find the value of all 6 trigonometric functions. So when it says exact value, that means that we want it as a fraction or a simplified fraction, not a decimal. So anything that we would have to round or we had to cut it off somewhere, that wouldn't be exact. So we don't want to use a decimal for these answers. Now I know that my trig functions involve all 3 sides of the triangle. So I do need to figure out what's the length of this other side. So the missing side is the one opposite the right angle. It's the longest side, so that's our hypotenuse. If you remember from geometry that with a right triangle, we can use the Pythagorean theorem to find a missing side. So if you remember that, we know usually a squared plus b squared equals c squared in terms of the way that we just labeled the triangle. Would be like opposite side squared plus the adjacent side squared equals the hypotenuse squared. So however you want to remember that, we're going to use that to figure out the length of the hypotenuse so that we know all 3 sides. And it doesn't matter which side is A and which side is B as far as adjacent and opposite, but C has to be the hypotenuse. It has to be long. All right, so first I'm going to find the length of that hypotenuse. So I am going to use it the way that I wrote it here. I'm going to take my opposite side, which is 6. And my adjacent side is 8. So 6 squared plus 8 squared should equal my hypotenuse squared. So I'm going to evaluate those. 6 squared is 36. 8 squared is 64. Thirty-six plus 64 is 100. So my hypotenuse squared is 100. Now to figure out the hypotenuse from this equation here, I know the hypotenuse squared. If I want to unsquare it, I'm using the square root. So I'm going to square root both sides. And you may remember from algebra that when you take the square root when you're solving an equation, if you introduce the square root, then you got to worry about that plus or minus and whether it's positive or negative. We're not worried about the negative here because what we're finding is the length of a side of a triangle, and that is not going to be negative in this case. So we talked about theta being in the first quadrant, less than 90 degrees. So all of the trig functions are positive. Everything's positive here. So I'm just dealing with the positive square root. And so square root both sides. On the left side, that gives me 10. And the square root of hypotenuse squared is just 1.5. So now we know the long side of this triangle is 10. So now we have everything we need to know to find sine, cosine, tangent, cosecant, secant, and cotangent. So sine was opposite over hypotenuse. And in this triangle, opposite side here is the 6. That is opposite theta. And the hypotenuse is the long side that we just found. So it is 10. So this sine value is going to be 6 over 10. And we're going to reduce that. Both of those are divisible by 2. So if I divide by 2 on the top, I get 3. And dividing by 2 on the bottom, I get 5. So in simplest form, the sine of this angle theta is 3 over 5. Cosine is adjacent over the hypotenuse. The adjacent side is 8. Hypotenuse is still 10. Reducing 8 over 10, again dividing by 2, and it gives me 4 over 5. Tangent is the opposite over the adjacent side. And that is 6 over 8. Reducing them by 2, I get 3 over 4. Now I find the other 3, if you remember which functions are reciprocal, you can just flip these over. But you can also use the definition. So cosecant is hypotenuse over opposite. This one is the reciprocal of sine. And it is 5 over 3. Let me go back to using the definition. Hypotenuse is 10, so let's start 10 over the opposite side 6. And reducing those gives me 5 over 3. So it is the reciprocal, you can see here, of sine. So sine is 3 over 5. The reciprocal, just flipping it over, is 5 over 3. Secant of this angle theta is the hypotenuse over the adjacent side. So 10 over 8, which simplifies to 5 over 4. And then let's squeeze cotangent down here. This is the reciprocal of tangent. By definition, it is the adjacent side over the adjacent over the opposite. So that would give us 8 over 6, which would reduce to 4 over 3. So there's all 6 exact values of our trig function. So let's do another example here. See if we can find the exact values. Here they give us an angle, 45 degrees. And of course, this one's on the unit circle, so we already know these, but want to illustrate that it matches up with the triangle definition. So you could also figure these out using a special triangle. And since we already know the unit circle, let's put this triangle on the unit circle. All right, so halfway between 0 and 90, that's our 45 degrees. So we know the coordinates here are square root of 2 over 2, and square root of 2 over 2. And if I draw my little triangle, so if I just draw a perpendicular from the circle to the x-axis, so that gives me our right angle. These coordinates tell me the horizontal distance, that would be my x. X tells you how far do you go left or right. So that's the horizontal distance. This distance here is my X coordinate. And then my vertical distance here is my Y coordinate. So the length of these sides are the X and Y coordinate of this point on the unit circle. And we'll see that that's true in just a moment. But since we're on the unit circle, we know that it's called that because the radius of the unit circle is 1. So I'm going to go ahead and label this side. The hypotenuse is the radius of the circle, and the length is 1. Now, another thing that I know about this triangle, because the one acute angle is 45 degrees, I know that all 3 angles in a triangle have to add up to 180 degrees. So if the right angle is 90, this angle is 45, the other one also has to be 45. They all have to add up to 180. So 90 plus 45 plus another 45 gives me the 180. 45 plus 90, 180 degrees. All the angles in a triangle have to add up to 180 degrees. So both of these angles are 45 degrees. They're equal to each other. Then the sides opposite them are also equal to each other. Whatever the length of this side is should be exactly the same as that side, which we can see from our coordinates. But if we're trying to figure out these numbers, say we don't know this, and we're just trying to figure out from this triangle the lengths of these two sides, first thing I know is that they're exactly the same. So when I'm doing my Pythagorean theorem, I don't have to say a squared plus b squared. I know a and b are the same, so I could call them both a or call them both b, whatever you want. So now, the only other thing that I would note here is that the hypotenuse is the radius of the circle, so it's equal to 1. So now I'm going to use the fact that these two equal angles have to have sides opposite them that are also equal. So the two sides have to be equal. I'm going to call them both a. And 1 squared is just 1. Let's do that. So now, if I'm calling them both a squared plus a squared, well, that gives me 2a squared. And now I'm just trying to figure out what is a. So trying to solve for a, first I'm going to divide by this 2 on both sides. So now I just have that a squared is equal to 1 half. And again, to go from a squared to just a, I need to square root it. So if I take the square root on both sides, a is equal to, so when you square root in a fraction, you can do square root of the top and square root of the bottom. Square root of the top is just 1. And on the bottom, I don't know the square root of 2, so I'm just going to write it as the square root of 2. So that's a. Doesn't quite look like what we have here for our coordinates on the unit circle. And that's just because it's not rationalized. We need to rationalize the denominator, which remember, I'm multiplying both the top and the bottom by square root of 2. I'm going to multiply by square root of 2 on the top and the bottom of this fraction. And that gives me the square root of 2 on top. And the square root of 2 times the square root of 2 is just 2. So effectively, I'm squaring it. So I'm undoing the square. I just end up with 2. So this lets me know that the length of both of these sides, since they're both the same, they both have to be square root of 2 over 2, which matches what we have from our unit circle. So the question asks me for sine, cosine, and tangent of these angles. And now that I know the lengths of these two sides, so imagining that I did not know the coordinates here, just from the triangle perspective, I can use the Pythagorean theorem and what I know about geometry to figure out the lengths of those sides. And then I can use these definitions. Sine of 45 degrees, that is opposite over the hypotenuse. The opposite side is the square root of 2 over 2. If I put that over 1, I still end up with the square root of 2 over 2. Cosine of 45 degrees, using my triangle, would be the adjacent side over the hypotenuse, which again is the square root of 2 over 2 over 1. And tangent of 45 degrees. Tangent is opposite over adjacent. So it's the square root of 2 over 2 divided by the same thing, which equals 1. So we can see that on the unit circle, but this just kind of illustrates that we can also create a triangle, a right triangle, and use the definitions that we learned in 1.3 to evaluate these.